Hi friends, in this video I'm going to discuss some applications of Gauss law so that you can appreciate the Gauss law even more better. The figure which you are seeing is a diagram for infinitely long charged wire whose charges are distributed equally. Say its linear charge density is lambda, and now I want to calculate the electric field for this kind of situation. So I'm assuming a Gaussian surface, which is a cylindrical surface here of length L and radius R. Let me tell you something. Let me take a point P here, which is at a distance capital R from this wire, and let me take another point P dash here or P2 here, which is at a distance again capital R from this wire, from this uniformly charged infinitely long wire. Now, I want to say what I want to say is that there is a symmetry here. See, the environment in which the point P1 is there is similar to the electrical environment in which point P2 is placed. So, the electric field at point P1 should be similar to something electric field at point P2. And take another point P3 here above P1, which is also at a distance r from this wire. Now, as this is an infinitely charged, infinitely long wire, the environment of P1 is again similar to the environment of P3. So, again the electric field should be something similar in both these cases. So, by using all the symmetry arguments, I can say that at every point around this wire, the electric field points in this direction. I mean, radial direction everywhere. And please note that there is nothing called as an infinite wire. But for our practical purposes, the central part of a very long wire, if you are dealing with the central part of a very long wire, you can treat it as an infinitely long wire. So now let the electric field on this Gaussian surface be E. So it will be E here also because the wire is passing through the center of the cylinder. So it will be E, just the direction will be different. Now, by Gauss law, the flux through this curved part of the cylinder is E into the area is the area vector is radial anyway at all the points on this curved surface. So the dot product will be just the product of this magnitudes. So my flux is electric field into the area is 2 pi r into L, and this is equal to the charge enclosed, which is nothing but lambda into L, linear charge density lambda into length L, by epsilon naught. This is from Gauss law, and now LL gets cancelled. So I get E is equal to lambda by 2 pi r epsilon naught. So this is how the electric field varies with radius or with distance in this situation of infinitely long charged wire. Now the direction is given by this thing because as I said, electric field lines go out of a positive charge and come into a negative charge. So if the same charged wire was of negative charge, then the field lines would have been like this. Just the direction of the arrows get reversed. Everything is same, and the magnitude is this thing. So let's move forward. See this situation. Here I want to calculate the electric field at a point which is at a distance r from a infinitely long or infinitely big sheet, uniformly charged sheet. And you can take the central part of a very big sheet, and when you're dealing with that small part, you can assume this situation to be, or you can assume that sheet to be infinitely long sheet. Now I'm assuming my Gaussian surface as this cuboid. Now let me calculate the flux again through this surface. Again, by symmetry arguments, my electric field is supposed to be like this here and like this here. So my area vector here points like this, and Flux at this surface, I get it as, let my cuboid has this area of this side as, let it be A, capital A. So, and electric field be E at this distance R. Here also let it be R. So, E into A gives me the flux here. And similarly, there is a flux here also. And here also the normal vector and electric field are parallel. So, these two get added up and the net flux is this thing. It is equal to the charge enclosed, which is the surface charge density into the area here by epsilon naught. So my E is sigma by 2 epsilon naught. So as you see this, you are not getting any R term in this. So it is independent of the distance you are from this infinite sheet. If the sheet were really infinite sheet, then this holds. So let's move forward. Let me tell you one more thing. I'm assuming this sheet to be positively charged. So my E is in this direction. If it were negatively charged, it was a negatively charged sheet, then my E would have been in this direction into the sheet. Let's move forward. Just take this note. See that all your calculations of how to find electric field are becoming easy just because you are applying Gauss law. Our next scene is this. Consider a sphere, uniformly charged sphere, whose surface charge density is say sigma. Now I want to find the electric field at a point P, which is at a distance r, small r, from the center of this sphere. So to find this, let me assume my Gaussian surface also to be a sphere passing through this point P. Let this radius of the shell be r, capital R. So let me find the flux. Let the electric field at this point be E by symmetry arguments. Everywhere the E will be pointing radially outwards. And throughout my Gaussian surface, since the radius is constant, E will be same in magnitude. And you know that area will be pointing outwards radially. So my flux becomes E into, let me write final step or the final area, 4 pi small r square is equal to total charge is the total area of the sphere into the surface charge density by epsilon naught by Gauss law. When this thing and this thing gets cancelled, I'll end up with E is equal to sigma capital R square by small r square epsilon naught. Here capital R is a constant because that is a solid shell, right? And if the total charge on the shell is Q, I can write it as 4 pi capital R square into surface charge density. So I'll replace sigma into R square with Q by 4 pi in this formula. I get E is equal to Q by 4 pi R square and epsilon. This is something we know. This is something we are familiar with. This is nothing but the electric field at a point which is at a distance r from a point charge q. So what can we infer from this? If you want to find a electric field at point which is outside a shell, then the entire charge on the shell can be treated, or this shell itself can be treated as a point charge with the same charge located at the center of the shell. So what if you want to find the field inside the shell, say at a point P dash inside the shell? So similarly, by similar method, take a Gaussian surface here, and you'll see that no charge is there inside this Gaussian surface. So obviously, the field at this P dash is going to be 0. Q by epsilon naught, since there is no charge inside it, the field inside shell is 0. And hope you understood everything till now, and that's it for today. Thank you for watching these videos.